Hey, all, good afternoon. We'll get started in just a couple of minutes while everyone gets on the webinar today. We'll wait about one more minute. All right, it's 12:01. I think folks are still coming in, but we'll go ahead and get started to make sure we have adequate time. Hi, everyone, and welcome to the Mid-Atlantic Biosolids Association webinar series. We're pleased to have you here today while we're talking about advancing stabilization processes. My name is Stephanie Spalding, and I'm with HDR in Virginia Beach, Virginia, and I'm your moderator today. I'm a member of the VWA Education Committee. I'm a member of VWA as well as the program committee for the Mid-Atlantic Biosolids Association. And I'm excited to be hosting this session. We have three great speakers today. The first is Chris Wilson, who's going to be presenting on THP implementation and Class A biosolids production within an operating Class B digestion facility. Our second speaker is Bill Barber, who will be speaking on the influence of thermal hydrolysis on carbon footprint and biosolids management. And then these two presentations are going to be capped off by a 15-minute overview of the Hermitage experience with food waste supplementation by Tom Darby. Before I hand over the mic to our speakers, I have a few housekeeping items to cover. First, be aware that your microphones are muted as an attendee and your video has been disabled. If you can hear me, you've done it right. Each presentation is going to be 25 minutes with 5 minutes for Q&A. However, any time during the presentation, please use the Q&A feature in the middle of your screen to ask a question by typing it. I will go through the questions and ask them with time allowing at the end of each session, and then we will be able to respond to them as they come in. So at any time, please do continue to ask questions. If you have any technical issues, please also use the chat feature and we can work to get them resolved. Today's webinar will be available as a recording after the live session. An email to the link to the recording will be sent out after the webinar series in mid-August. So without further ado, I'd like to kick things off by welcoming our first speaker, Chris Wilson. Dr. Christopher Wilson serves as Chief of Process Engineering and Research at HRSD. In this role, he supports process engineering and optimization activities at HRSD's treatment facilities, as well as managing specific projects within HRSD's applied research program. Prior to joining HRSD, he worked as an engineering consultant who focused on wastewater process engineering and solids processing after receiving his PhD from Virginia Tech in 2009. He is a licensed professional engineer in Virginia. And for those of you all who might not be aware, HRSD is the Hampton Roads Sanitation District in southeastern Virginia. So Chris, over to you.
Hi, everyone. I'll bring up my presentation here. The always clunky transition to PowerPoint.
You see your desktop there? Yep.
All right, we should be on title slide. Let me know when I get there.
We're on title slide.
Okay, cool. All right, thank you, and thanks for your patience getting this open. As Stephanie mentioned, my presentation is about really the startup and the early operation here of our Class A biosolid system at our Atlantic treatment plant down in Virginia Beach, and doing that while maintaining the operations of the Class B facility to process solids and get biosolids cake out of the plant. So this is I touch a bit on the overall biosolids management program as a justification for the project and understanding where this fits into HRSD system. And then I'll also talk about the more specific THP at Atlantic treatment plant and why we're doing that and how the data are coming along. Before I go into the presentation too much, I do want to acknowledge that I'm presenting this project. It was my first project that I picked up at HRSD, and it's just been wildly successful to date. HDR and Brown and Powell were the designers. Our moderator, Stephanie Spalding, was the design project manager. It was a CMARC project delivered, Crowder being the construction manager at risk. Cambi's been fantastic to work with through the project. So, and of course, our operations and maintenance staff at the treatment plant have been instrumental in the design and bringing it online. So this is a multitude of people that have contributed to the success of this project to date. So I'll talk about our solids management program overall. As Stephanie mentioned, we're here in Southwest Virginia or Southeast Virginia, coastal Virginia. Our Atlantic treatment plant is located down here on the Atlantic Ocean. It's our only ocean outfall treatment plant. And we have these 9 larger treatment plants. And our definition of a large treatment plant is anything over an MGD. Probably our smallest treatment plant on this graph is either Iron Base or Williamsburg, depending on the day of the week. And those are 8 to 12 MGD flows on a dry weather day. Atlantic runs up to about a 54 MGD plant. So this is a fairly large treatment plant for Mid-Atlantic standards where we're implementing this project. So we operate our 9 large treatment plants that manage solids in one of 3 ways. We have multiple hearth incineration at 5 plants currently. We have biosolids land app through Class B acid gas anaerobic digestion at the Atlantic plant historically, and that's actually still in operation. And then we have contract composting for 2 of our plants, our James River and our York River treatment plant. So I'm going to walk through our proportionality of how we use these 3 strategies to talk about where we're going over the next couple of years and point out the criticality of a successful startup and a good fate for the biosolids fertilizer produced from the Atlantic plant when thinking about our long-term biosolid strategy at Atlantic. So in the next couple of graphs, this is sort of a legend here on the bottom. So I'll have a number of bubbles, and they correspond to these colors up on the top. And so black is multiple hearth incineration, green biosolids land app, and brown is contract compost. And the size of the circle that I'm showing, I'll show a circle for each plant, and the size of the circle is relative to the dry tons per day produced by that treatment plant. And then below that, I'll sum up the area of all those circles, so you get kind of an idea of what HRSD is doing across the board from a allocation of solids into these 3 buckets. Okay, so here's where we stand today. As I mentioned, we have 5 multiple hearth incineration plants, and our Nansemond plant, one of our additionally larger plants, transports biosolids cake from a Class B digestion process over to our Boat Harbor treatment plant for multiple hearth incineration too. So we have 6 plants allocated to MHI. We have the 1 plant doing biosolids land application and 2 plants doing contract compost. So that's where we sit as we are here in 2020. We have some changes to our program that are pretty well defined up through 2025, and I'll walk through those. So our Chesless plant's coming offline in the next year. The wastewater is going to be transferred over to the Atlantic plant. So that's going to proportionally increase the size of the Atlantic flow and take one of our multiple hearth incinerators offline. So Cheslow's goes away, Atlantic gets bigger. Then we're removing one of our incinerators from service at our Army-based treatment plant. And those biosolids are going to be, or those raw dewater or raw thickened solids are going to be transferred over to the Atlantic treatment plant, and potentially some to the VIP treatment plant too. So again, one of our incinerators goes away, Atlantic gets proportionally longer. So you start seeing we're achieving a couple of things here. One, we're starting to balance those bars, taking some away from multiple hearth incineration and increasing biosolids production, but also we're sort of balancing out and making the biosolids program a bit more important to us. And so here's where the plot really thickens. In 2026, about January 2026, we're projecting the Boat Harbor treatment plant is slated to come offline. And raw wastewater from Boat Harbor collection area is going to be transferred across the James River to the Nansemond plant. And so I mentioned earlier that Boat Harbor is the furnace that burns Nansemond solids. And so not only am I increasing the amount of Nansemond solids, I'm taking away the place that those solids are currently burned. And so this brings a big question. What happens to the combined Boat Harbor and Nansemond solids when that occurs in 2026? And so we have a couple alternatives for thinking about the fate of the biosolids at that point. And so I'll walk through those real quickly. So we could increase contract compost. We could take all the material from that facility, the larger future Nansemond, and send it to contract compost. That looks really nice from a balance standpoint. Relying on contracting mechanisms and external partners to provide the composting service. We can expand the Atlantic THP system. So up until this point, the Atlantic THP system, as designed in 2020, has the capacity to deal with the Cheslow's and the Army-based closure, the Cheslow's closure and the Army-based solids transfer. What it doesn't have capacity to do is to take over Boat Harbor and Nansemond. And so that would be a pretty substantial capacity expansion at Atlantic if we were to do that. And then we could do something else at Nansemond. We could do a drying and pelletization facility at Nansemond if we chose to do that. Some other alternatives, doesn't have to be pellets, but that's an example of something that maybe fits at that site. And so all this is being vetted at really in real time right now. We need to make some decisions on the future of Nansemond, space allocation, what recycle streams need to be managed. And so really this is all coming to the point in fall 2020 where we have to understand what our capacity is at our treatment plants and where we want to go with our solids out into the mid 2020s. Looking at us on a capital and life cycle costing basis. And what it means is we need to understand the startup and the product that we're producing at Atlantic from the THP process, so that we can start at least thinking about being able to market and distribute or land apply. Frankly, all of that cake, this circle here is quite large. And so we need to make sure that we have a good way to get that material out of the plant and used in a beneficial way. So now I'll talk a little bit about the how we're actually bringing the system online at Atlantic. And there's two things I want to talk about. One is our Class A demonstration process and the actual startup of how we're doing Class A startup during a Class B operation. And then a little bit of data from actually just pulled this morning to show you how it's going. All right, so this is step 0. So this is what we do at Atlantic circa 2 months ago. So I mentioned Atlantic is a Class B biosolids system. It's acid gas anaerobic digestion. The acid gas system is really driven for foam control in the anaerobic digesters, but it's an acid gas digestion system. So 4 primary digesters, typically online, split. So the top is going to be digesters 3, 4. The bottom is going to be digesters 1 and 2 throughout all these graphics. There's a combined digest sludge storage tank, final dewatering, and then we have 2 big storage pads out at the site. And so this is where we generally were before the startup. All right, so then we take we take digesters 1 and 2 offline, run class B through digesters 3 and 4. Everything looks very much the same on the back end, but we're doing modifications in digesters 1 and 2 to upgrade, gas manifolds and things like that for higher loading associated with THP on the front end. Okay. And so then we put THP into service, and we started bleeding a little bit of solids off into digesters 1 and 2 through the THP system, pre-dewatering, using centrifuges before that. We also seeded the system, the digester 1, from an operating full-scale THP system at DC Water. So that's a little bit unique from other startups that have occurred in the States. And the reason why we did that is we have a distinct interest in achieving Class A solids quite early, and also the ability to stabilize digester operation early on based on the seeding from a high ammonia THP anaerobic digester at DC Water. And so that's a benefit to us in doing that. So we're in this mode right now where we're feeding digester 1, feeding digester 2, both getting thermally hydrolyzed sludge or THS. They're blending going to the digested sludge storage tank with Class B solids, going through final dewatering, and then everything that goes onto the pads right now we're calling Class B solids. We're not taking credit for the time temperature that occurs in the THP process, and we're not looking at fecal coliform measurements for the purpose of demonstrating that we are Class B or Class A, because we know that we have solids going through a Class B process right now. Okay. So then at some point, we're going to go through the process of modifying. So now we've gone through full ramp up. All the solids from the treatment plant are going through THP, being fed to digesters 1 and 2, and maybe we're a month or so from this phase. Then at that time, we could bring down digesters 3 and 4. We just had a meeting this morning talking about bringing down digester 3 in maybe about 2 weeks. Bypass the digested sludge storage tank, going through final dewatering, and then sequestering the solids that go through the process onto one of the pads. In the meantime, what are we doing? We're modifying digesters 3 and 4, beginning construction there, just as we did on digesters 1 and 2. We're disinfecting the digested sludge storage tank, so anything that goes in there isn't going to have repopulation with fecal coliforms. And we're actually spray disinfecting the storage pad B. And so this is just disinfected high chlorine residual NPW that we'll capture and go back to the plant on pad B. Okay, then we transfer back to the digested sludge storage tank through final dewatering. And now we're back on storage pad A. And we're calling this again Class B, right? And so you say, we're going through THP, we're going through a disinfected digester, through a disinfected digested sludge storage tank, through final dewatering, which we've also done a good job of cleaning out the centrifuges in operation, all the conveyor systems, even down to the point of cleaning the tracks on the front loader that moves cake around the pad. So you say, why is this Class B material? Well, it's Class B material because it's still on the undisinfected pad, and we're going through an agreed upon demonstration period with DEQ to demonstrate that what's falling onto the pad is indeed Class A. So when it gets transferred over to a disinfected pad, we have Class A material that's able to go out as such. And so this was a really nice collaborative process with Virginia DEQ to develop the demonstration phase to show that we could produce Class A solids. I think a key point in this is the system, because we're continuing to go through Class B, was not considered a new source. And so we didn't have to demonstrate Class B through this process either. So the key statement here is all biosolids generated during the demonstration period shall be land applied as Class B biosolids until all samples collected over 12 weeks contain less than 1,000 mpm per gram fecal coliform. And so it's going to be based on, our demonstration schedule is going to be based on fecal monitoring and time temperature recording in the THC batches that we're going to, that we currently capture on our SCADA, our DCS system. You could see our sampling period ramps down over a period of weeks. And so 3 samples, 2 samples, 1 sample per week each for 4 weeks. So this is a 12-week demonstration period. I really appreciate where we got to in this process, because what DEQ is saying to us is that you have to have 12 weeks of compliance. If you have a hiccup, you're going back to the beginning. And they very clearly lay out to us what's required to demonstrate class A with certainty, and really put it on us to make sure that we're ready and able to do that. And so that is as clean as you can hope to be for a demonstration period, I think. And of course, as you can imagine, we're able to do volitional testing on the THP side of the system right now to make sure that we're ready to do that testing. We're not just marching into that blindly. Okay, so now we have Class A solids. All the solids going through THP, through digesters 1 and 2, digested sludge storage tank, final dewatering, and now we could transfer over to the disinfected pad, and we would expect that the pad's not going to recontaminate the Class A solids, and then the material on that pad would then be subject to our Class A land application or distribution and marketing permit. And at this point, we could actually take material from that pad and begin playing with it, experimenting on generating projects for potential distribution and marketing. And then, because digester 3 and 4 are offline, we only have one THP skid. It's a Cambi B64. We would split solids between probably 3 online digesters at that point, digesters 1 and 2, and either any 3 of the 4 online, going through the digested storage tank through final dewatering, and then they could go on either pad, because we will have disinfected pad A at that point. And so now we have a full running Class A process with all our facilities available. This is a really important time step, because this means we're really available to manage additional load through the from Cheslers and Army Base. And in many plants, THP capacity or digester capacity may be limiting factors. For us, we could handle a lot of solids in 2 digesters. These are pretty big digesters at the Atlantic plant. So whether or not we need the 3rd digester in operation, I think it's comfortable to have 3 digesters in operation. Our THP system is plenty big for the load from Cheslers and Army Base coming over. Really, where we want to get to is we want to have 2 pads available, because that's producing a lot of cake. And we've not seen that material yet. We don't know exactly how it stacks. It's going to take some time to just see the material, and so we're really eager to get both of our pads available, so that we could play around a little bit with some Class A material and thinking about final products, while still having plenty of space to stockpile material for annual land application. All right, so I was saying this morning that you could do things that you would never do in front of a presentation room on a webinar, like show a screen grab from DCS. But because we all have our computers in front of us, bear with me here. But I want to show a couple time points on the startup of Digester 1. I mentioned we started up Digester 1 using seed material from DC Water. We put about 200,000 gallons of solids into a 1 million gallon tank, and then the rest was filled up with disinfected NPW. And so it took some time to ramp up feed into the system. That occurred back in early May, and so I'm showing from mid to late June up to this morning on this plot, and a couple of markers of what happened. So we were ramping up over time, and we got a little aggressive in our ramp up. And this is not atypical of THP startups where you have low ammonia conditions for some period of time, and then you start ramping up solids. Ammonia concentration gets quite high in the digester, and methanogenesis suffers for some period of time. And so this is what we saw right about the end of June. And so the green line here is digester gas production in the digester. And so this is going to be relative to how much feed we're actually giving it, as well as the health of the methanogens. And so this green line dropping off was obviously not something that we wanted to see. And so methanogens sort of took a nap here. We continued feeding it for a couple of days. And then decided we took a break for maybe 2 weeks and cut off feed to the digester here. And it took some time, and I will say a bit of faith that the digester gas was going to come back. We started feeding just a little bit of THS right around the 4th of July. The purple lines in the back are how much we're feeding, and so there's just a relative scale. So you can see we've brought back feed a little bit here, and then we've been ramping up feed slowly over time. We got really excited when the methanogens woke up back here and they started producing gas, like way more than we would ever expect. But that's sort of a false indicator, because what we're getting gas production up here is really all this feed that we've given the digester back here that was being pent up as VFA. And so we got volatile fatty acids, acetate concentrations up into the 6,000 milligrams per liter until just over maybe 4 or 5 days. The methanogens chewed through all that and started producing biogas. And so again, we're feeding constantly, and then the biogas ramps down. And so this is just maybe getting down to a real indication of what the gas production is at our feed rate without all of the VFA pent up in the digester. And then as we've been feeding, feed's gone up, digester gas has gone up, things are quite stable, the digester looks great, low VFA concentrations, and we're pretty well at steady state on the digester. We'll probably be full feed on it in about a week. Digester 2 has been getting spillover from Digester 1, and so startup is really undramatic because everything that Digester 1's overcome, Digester 1 doesn't have to, Digester 2 doesn't necessarily have to see just yet. Nothing too exciting there. All right, so the conclusions: THP system at Atlantic is really a crucial element of our biosolids program. We're in the middle of startup procedures allowing uninterrupted operations for solids management and biosolids production at Atlantic. We'll begin our demonstration period for Class A biosolids at Atlantic very soon, and we're excited for that. Once we have Class A solids to play with, we'll begin experimenting with products for distribution and marketing. And the peripheral elements to THP have been the biggest challenges, so pre-dewatering has been a bear. There's no joke about that. Pulper feed dilution is just something that's new to us. Some challenging programming and tuning there. But I'm not going to invoke the wrath of fate by stating in writing how the overall startup, I almost did it, how the overall startup has gone so far, and I'll just let you guys read between the lines on that one. With that, I think we have a couple minutes for questions.
Great, thank you. Thank you very much, Chris. As stated before, there is a Q&A button in the middle of your screen if you hover over it, and please ask your questions there. We've got 2 coming in so far. The first is the Atlantic plant biosolids being managed internally, or is it outsourced through a full service contract? You have incinerators and contract compost. Is the ultimate goal to be self-managed or full service provider structure?
So it depends on what you call for full service. So the what we have right now is a contractor that manages the cake on the pad and manages our land application of Class B material. That's the plan going forward. And I don't know that we've made a final decision on what our distribution and marketing looks like going past that. So in the past, if you remember, HRSD had a composted product that was contract composted, but managed from a distribution and marketing internally. And so I think there are a lot of things that are potentially on the table going forward. But our current model right now is a contract service provider managing land application, and that'll be at least where we are initially.
So a related question is, for the Class A product marketing, are you developing that in-house? And if so, are you adding staff for that purpose?
Fantastic question. Yeah, I mean, so yes and yes. That history of marketing the NutriGreen product didn't market itself, right? Rhonda Bowen is a Jedi of biosolids marketing, and there's no joke that her work was instrumental in making that a successful product. And so we remember that model, and I think we know what works there. And so there's not commitment necessarily to bring on a recycling manager yet. There's a lot of conversation about that. I think that's still to be determined. We have done a study with Ron Alexander looking at marketing alternatives in the area. And so we sort of have a feel where we want to take our product initially, relatively lower intervention. And because we have the Class A land application available to us, it's not hugely urgent that we have a distribution and marketing program, but we want to move there without dallying necessarily. But I would say we'll form up our opinions maybe this time next year about where to take that and how to populate internally.
All right, thanks, Chris. So that's all we have for right now from Chris. If you have any more questions for Chris about the HRSD project, please continue to type them in the Q&A. And if we have time at the end of the session, we'll circle back. So thanks, Chris. If you go ahead and stop sharing, and Bill, if you could start sharing your screen while I get you introduced. So our next speaker is Bill Barber, and he's going to be presenting on the influence of thermal hydrolysis on the carbon footprint of biosolids management. Bill is a technical director for Cambi based in North America. In this role, he develops biosolids projects and assists with research. Prior to this, Bill worked for AECOM in both North America and Australia, providing consulting services for biosolids projects. And previously, Bill worked for the UK's largest water utility, United Utilities, in a variety of strategic, technical, financial, and research roles related to biosolids, and was instrumental in the development of Europe's largest thermal hydrolysis project. Bill is a reviewer for several peer-reviewed journals and author of IWA's forthcoming book on thermal hydrolysis. He has a PhD and degree in chemical engineering and is a chartered engineer. So, Bill, please take it away. Thank you.
Thanks very much, Stephanie. And before I start, I'd like to thank everybody connected to Marber, Bill Toffee, and Stephanie. Thank you very much. And also to Chris for an interesting presentation. Today, I'm going to talk about thermal hydrolysis, a bit about carbon footprint of biosolids management. And I'm going to look at a case study of HIAS, which incidentally was the first commercially operating thermal hydrolysis plant in the world in 1995. I don't really need to go too much into the background of carbon footprint and climate change. Every time we put the news on, we see record droughts in Africa, we see record fires in Australia where the smoke from which reach South America. Each typhoon season is worse than the last. And even just last week, I read this article, there was a heat wave, temperatures in excess of 100 degrees Fahrenheit in Siberia. I didn't think I'd read that in my lifetime, and that was last week's news. So, the decisions we make have an impact on the environment. Everything we do, the power that we consume, the cars that we drive, the food that we eat, the sports that we follow, the buildings that we use, everything has a carbon impact, carbon footprint. This carbon footprint could be further subdivided into various categories. There's an embodied and an operating carbon footprint. So by embodied, what I mean there is the carbon footprint associated with constructing something. So everything, if I have my mobile phone, the materials of construction of that phone has a carbon impact. And then the operation of something will have a carbon impact with the chemicals I use, the energy I use, these all have an operating carbon footprint, a bit like CapEx and OpEx when you're looking at financial calculations. Also, there are indirect and direct carbon footprints. Indirect carbon footprints are, for example, the power we use in our home. We are not generating the carbon footprint ourselves. The power station indirectly is generating that carbon footprint on our behalf. So the decisions we make on how much power we use will influence how much carbon footprint is generated at that power station. So this could be, for example, kilowatt hours for pumping or mixing digesters will have an indirect carbon impact. From a direct perspective, we get process emissions. So these are actual greenhouse gases, a number of greenhouse gases that we generate and go to the atmosphere. For example, we can generate CO2 we store sludge, we can generate methane. Nitrous oxide is generated from deammonification systems, which may affect its sustainability. So these are the direct gases that then go straight into the atmosphere and have a carbon impact. On top of this, there are owned and influenced carbon footprints. So owned carbon footprints are things like, if I have a treatment work, so we just heard about Chris's treatment works, the decisions you make on your site generate a carbon footprint. Other decisions, you influence the carbon footprint of other manufacturers in your supply chain. So I can choose to have a polymer that is sourced locally, or I could choose to have polymer that's coming from China. These will impact on the carbon footprint. So all of these things need to be considered when we're looking at carbon impact. Going a bit more into detail on the embodied carbon. So really here we'll design something. So we design, say, a thermal hydrolysis plant, and we work out how much steel there is required. That'll give us our quantity of material. Then that material has to be manufactured. That consumes power and it generates direct emissions. And then that has to be transported to the site, which will generate further carbon footprint from fuel consumption. And then ultimately, when that's disposed, when you buy a car and then you throw the car away and it's trashed or recycled, that also has a carbon impact. So it's a carbon impact from the cradle, from the birth of that material until it's reused or thrown away. And here is a graph of embodied carbon footprint versus materials. Typically, natural materials have a very low carbon impact. So things like sand and soil, asphalt, stone, things like this. The more processing you put in, the higher the carbon footprint. So things like clay pipe, bitumen, bricks, cement, concrete have a higher carbon footprint. And then here on this side, on the right-hand side, you see things like fertilizers, which have a very high carbon impact, aluminium, or aluminum, I should say in America, stainless steel, copper, polymers for dewatering. These are very high carbon footprint materials, methanol, things like this for denitrification. So if we look at a car, for example, the embodied carbon footprint of a car is based on the construction materials, so metals, plastic, grass, the rubber on the tires and various things. And for hybrid cars, the exotic metals in the battery. Then you put gas in it and maintenance, and then you have your operating carbon footprint. And there's an example there. This is based on American, very low miles per gallon car. It can be between 2 and 4 tons of CO2 equivalents per car per year. That's an example. Looking closer at carbon footprint of biosolids management, we have wastewater treatment. Wastewater treatment consumes power. So as I mentioned before, this could be through aeration or pumping. Any kilowatt hours we're consuming, this is an indirect carbon footprint. Chemicals, polymer, ferric, natural gas, if you will. Emissions, this could be direct emissions, typically from biosolid storage or wastewater. But on the positive side, we can generate a renewable energy. Then we get our biosolids that biosolids has to go somewhere. So there's an element of fuel consumption depending on where it's going. And depending on the outlet, whether, as Chris mentioned, it could be incinerated or it could go to agricultural land. There are emissions. These are different emissions depending on the different outputs. There's displacement of various things. For example, if I put a pound of nitrogen in biosolids, that displaces a pound of nitrogen fertilizer. I can sequester carbon if it's going onto the soil. So there are various benefits there. And when we add all of that together, we add that to our embodied carbon footprint, and we'll get our carbon dioxide equivalent, so our whole life carbon footprint, if you will, for a biosolids project. Unfortunately, most of what we do today was designed a long time ago. If we look at wastewater treatment, if we look at screening, primary treatment, thickening, dewatering, thermal drying, nutrient recovery, all of these have history in the past. All of those things I just mentioned were invented by the latest 1860. So, you know, a lot of what we do is by design not suboptimal. It's not ready for today's modern drivers, such as carbon footprint. So when we're looking at water conservation, energy recovery, nutrient recovery, or even carbon footprint reduction, by default, what we do today is not efficient. It's by design. So there are a lot of things we can do to enhance the performance of today's infrastructure, which was designed when people were falling sick of cholera and typhoid. People weren't concerned about carbon footprint in 1850. So we can look at a number of technologies. We see these such as thermal hydrolysis. We see deammonification, for example, which can take existing infrastructure, which has a long lifetime and life cycle, and make it work in a way that it's not designed to operate. One of these is thermal hydrolysis. I'm not going to go into too much detail here, really to say that it's pretty much considered a mainstream process now. There are about 130 plants in the world. Cambi, who I work for, operate maybe just over half of those and about 3/4 of the world's capacity. Size ranges from 10 to 450 dry tons US per day. And even just a couple of weeks ago, Hong Kong now has signed a contract to have thermal hydrolysis in front of incineration. So, you know, thermal hydrolysis is almost really pretty much a standardized unit operation now. In terms of thermal hydrolysis and carbon footprint, there are a number of things thermal hydrolysis does or allows that enhances carbon footprint. First of these, it allows a higher loading rate in your digester because you can have more sludge going into existing digesters. You don't need to build as much digestion capacity, which lowers the embodied carbon footprint of construction of digestion. If you have existing digesters, you can create capacity in those digesters, and then you can divert organic waste which would have gone to landfill and had a huge carbon footprint. You can divert those to have more a waste management system rather than a sludge management system. And the carbon benefit of doing that is enormous. The performance of digestion improves, which means you generate more renewable energy to offset your scope 2 indirect emissions. I have less biosolids coming out of the digester, which means I have less transport and downstream processing. So irrespective of what happens to that biosolids, whether it's dried or burnt or goes to land or even goes in a hole in the ground, there's less of it, there's less impact. Dewatering is better, it means there's less water in the cake. So if I have a dry or an incinerator, the energy balance is going to be far superior. So there's less energy required in those systems. There's also less transport to go to outlets. And finally, the quality of the product is better. So this opens up, if you're going to land, this opens up new outlets, which means I don't have to transport the biosolids as far. There's less transport, less material for less transport, better stabilized, fewer emissions on the land. All of these together will provide the lowest carbon footprint, irrespective of the outlet of the biosolids. It's not just me saying that. There have been a number of independent third-party studies that have said this. You see here's a European Union document, the second one there from the left. The fourth and fifth ones there are from the Asian Development Bank. They did a work there looking at carbon footprint of biosolids management. And from my experience traveling around the world, China is by far the most serious in terms of carbon footprint reduction regards biosolids management that I've seen. That was the major driver for the project in China. Whereas in other projects I've worked on, it's been a nice thing to have. It's been a positive thing, but not the major driver. I'm going to talk briefly about carbon model that I've used for today's presentation and other work that I've done over the years. There's two aspects. As I said, the embodied carbon. There's an Environment Agency model, which looks at the embodied carbon based on construction. So depending on the size of the project, it looks at travel to and from construction workers, the size of temporary installations for those workers, the carbon footprint of those, the construction materials that are used. I use something called the Inventory of Carbon Energy from the University of Bath, who have done that in conjunction with the Carbon Trust in the UK. And that's basically a big database of carbon footprint of materials. And then I look at the operating carbon, the operating carbon footprint. There's an equivalent of Worth in the UK who developed a model in 2005, but it became quickly apparent it wasn't detailed enough. So I added a lot of layers of calculations to that model. It's basically a site-wide mass and energy balance, which looks at all the consumables, power consumption, direct and indirect emissions, calculates various things, and then compares and then converts that into a carbon footprint. So really what the operating carbon footprint model does, it looks at contributory factors such as power, emissions, consumables, all the things that increase carbon. It looks at all things that decrease carbon, such as power generation, displacement of fertilizer, sequestration, vehicle use reduction, and then the difference of those is the operating carbon footprint. So we'll look at a case study now, looking at those models based on a case study. This is a HIAS. I mentioned this project because it's been running for many, many years. It's the first thermal hydrolysis plant in the world. But it's based here, if I show you a bit closer, this is Lake Mjøsa. Norwegian government were very concerned about the health of this lake. In the early 70s, there was a lot of runoff, agricultural runoff, phosphorus going into the lake, industrial runoff, wastewater. So they set up HIAS, which is actually based of 4 separate water utilities, and they made a wastewater treatment plant with advanced phosphorus nutrient recovery and removal to protect this lake. So this had a very specific space in the Norwegian wastewater industry, very high profile plant. It's used for, looked at a lot of innovative technologies, and it's used for operator training. So that plant in HIAS was set up in 1974 to look after this lake. The sludge until then, the biosolids was applied to land, but there were concerns about the long-term application to land with metals and other materials in the sludge. So they wanted to look towards a more Class A solution. As I said, it's the world's first thermal hydrolysis plant. These are some typical numbers there. These are the current numbers. There's been a lot of changes over the years. Those numbers come from the clients themselves. There are a lot of teething problems with technology early on, but subsequently now they're very happy with the plant, and they've recently, just last year, upgraded the plant. So quickly going into the history of this plant, so in 1974, HIAS was established. They started looking at thermal hydrolysis in 1990, and in 1995 they put in this thermal hydrolysis unit, which by today's standards would be similar size to the one in Ohio in Medina, so it would be a B2 equivalent. It was about 10, 12 dry tons per day. What they did at the time was they put a new thermal hydrolysis plant plus mesophilic digestion plus a drying plant. There was no cogen. And the reason was they were concerned about the backup plan for the thermal hydrolysis. There were concerns about increased ammonia being released in the digesters, therefore the biosolids would have less nutrient content, so it may influence its use on land. There were also concerns that thermal hydrolysis plant wouldn't work. So the dryer was there as a backup plan to provide the Class A biosolids in the event that the thermal hydrolysis would fail. So the gas produced from the digesters would be used for running the drying plant. Other reasons the dryer was put in was to lower transport costs, and also with a pelletizer to provide a range of outlets to provide to minimize risk to long-term use of biosolids. Having said all those positive things about the dryer, that it failed, and in 1998 they decommissioned the dryer. There are a lot of problems with the handling of the sludge, sludge sticking onto surfaces. So in 1998 the drying plant was switched off, and a cogen plant was now installed to deal with all the excess gas that was being generated. In the year 2000, there were also some issues with the centrifuge plant that went in. There were issues with that, so a new belt press plant was put into there. In terms of thermal hydrolysis, the operating temperature was reduced around about 2005. It started off at 180 degrees C, because people are just working out what worked, and it was decided to reduce the temperature, and it found after 10 years, so it's a pretty conservative decision, and it was found that reducing to 160 had no impact on the performance of anything. THP was upgraded in 2007. From 2000, there was increasing loads to the plant and biological nutrient removal, which deteriorated the performance of dewatering. It was not the fault of the belt press, but dewatering reduced by several percentage points in that period. So a Buka press was installed in 2012, and it took 2 years to optimize. By 2014, the dry solids coming out that press was 38%. In 2016, the cogen plant was decommissioned and a new biomethane plant was put in. So this is an interesting project because it's looked at 3 different types of dewatering over the years and 3 different uses of the biogas, from drying to cogeneration to biomethane. And looking at the carbon footprint over the years, this is the initial upgrade in 1995. You can see most of the carbon footprint is associated with the concrete, and much less to do with stainless steel. The stainless steel is about nearly 20%, a bit less than 20% of the carbon footprint, but by weight, it's only about 3%. As I said, stainless steel has a much higher carbon footprint than concrete. So if we look at it by where it's coming from, most of that is a digestion plant because of the concrete. PHP, very low weight compared to the concrete, but very high carbon footprint for construction in comparison. So what I've done here is to look at the contributions of carbon over time. You see here the different time periods. These are I've simplified this, otherwise there'd be too many parameters. Well, I've simplified this into direct emissions, which are the dark blue, chemicals, which are the green. So lime was being used in the baseline, you can see there. Electricity, so indirect electricity emissions, which is the yellow, and red is transport. So you can see when the dryer went in, the transport element almost disappears, but there's a large gas requirement, the gray. And that gas requirement is because all the gas is being used in the dryer. So that gas is to power the thermal hydrolysis. That gas requirement reduces over time as the dryer was shut down, and also as process optimizations were made over the years on the thermal hydrolysis to reduce the steam consumption. But it went up again when the biomethane plant went on, because now the biomethane is taking the gas. So we need gas again for transport. For the thermal hydrolysis. Well, you can see here, transport really doesn't make a big deal in carbon footprint unless you put all the biosolids in a plane and fly it off somewhere, or put it in a rocket and fly up to space. It really doesn't have a big carbon footprint. So really, from an environmental perspective, putting in the dryer was far worse for the environment in terms of the gas it consumed, rather than the transport emissions that it reduced. Electricity consumption is insignificant in this example, and that's because of the energy mix in Scandinavia, which is extremely clean. So we look at the carbon footprints over time in terms of not contributions. These are the benefits. The main benefits are fertilizer displacement, which is great. That reduces when the digestion plant was there because you've got less biosolids. You can see there the biogas electricity generation is almost insignificant. Again, you are displacing a very clean source of energy in Scandinavia. And you can see here with the biomethane, that's a much better thing to do. Because now with biomethane, you're displacing dirty fossil fuel energy for vehicles rather than very clean, almost renewable, 100% renewable energy from electricity in Norway. So if we look over time, we can see here, initially the carbon footprint went up because the drying plant was installed, but with subsequent changes to the system, and especially the biomethane, the carbon footprint has massively gone down. This is based on Norwegian energy mix, which is extremely low carbon impact per kilowatt hour. You see there 0.015 kilograms of CO2. Coal is almost 1 kilogram per kilowatt hour in comparison. So this is almost zero. This is, this is cleaner than biogas. If I plot that data based on the average US energy mix, you can see the graph there on the right. So you can see there a much higher carbon footprint, which reduces with time. So the energy mix, how dirty the energy you're displacing is a huge impact. This graph here looks at the time period from 1995 to present. So the dark blue there is what if you continued going to land and didn't do anything, and the green is all the various things that happen to the plant. So you can see here initially the carbon footprint goes up because of the construction and the installation of a dryer, so it goes up even more, and then it starts to go down. But it takes many years to catch up with the do nothing scenario. So it becomes carbon neutral in 2008, and it takes about 19 years to reduce the carbon to the level it was when nothing was altered. But you can see now, as soon as a biomethane plant was installed, that it's just leaving the original solution behind in the dust. This is the same graph if I plot it on a USA energy mix. So if the calculations were done here rather than in Norway, where the energy is very clean, this is what that would look like. And it gives a completely different perspective. So here it breaks even within months of construction, because now the carbon footprint of the do nothing scenario is so high. It's carbon neutral within 5 years now, instead of what we saw before. So you can see this is hugely different. Quickly before I finish, I talk about a delay in decision making. So now what I've done now, this is based on the US numbers, added a 5-year delay before the thermal hydrolysis plant was installed. This is a very big issue because the infrastructure of wastewater treatment has a very long life cycle. We don't build digesters to demolish them 10 years from now. We build them to be in the ground 50, 60, 70 years into the future. So the decisions we make now have long-term environmental impacts. Even if we have a short delay, we can significantly lengthen the time before we're reaching carbon neutrality. As I mentioned, on the US data, we'd be carbon neutral within 5 years. If I put in a 5-year delay, I'd reach carbon neutrality 26 years from now, just to accommodate the cumulative emissions that I've generated. So it's really a big deal, the timing. So if we can see here, to summarize the Norwegian energy mix, the baseline, it was just about carbon neutral, and the actual solution to date, this is looking at the total carbon over the total lifetime of the project. You're reducing the carbon footprint by about 0.2 tons per ton of biosolids. If we did that on a US energy mix, we'd reduce the carbon footprint by about 0.1 ton, but if we didn't do anything, we'd be increasing it by 0.7, which is similar to using coal. Looking at the US numbers, if I looked at the carbon footprint, total carbon footprint, I'd actually have a massive carbon footprint if I added that 5-year delay. So timing is of the essence, really. So to summarize the influence of thermal hydrolysis on biosolids management, the decisions made by water utilities have an environmental impact. And this is more important because a lot of the infrastructure has a very long life cycle. And a lot of it wasn't designed for carbon reduction. Anaerobic digestion and thermal hydrolysis with anaerobic digestion plays a fundamental role. It reduces the amount of biosolids, increases the production of renewable energy, and both of these have huge positive impacts on the carbon footprint reduction. And finally, I'd like to conclude with the timing. Timing is critical. We see every day on the news the issues related to carbon footprint. Delays in decision making today will have very significant and fundamental long-term impacts, making longer-term, intermediate and long-term carbon targets much, much more difficult to attain. And with that, I'd like to thank you for listening and put in a plug for the book, as Stephanie mentioned, and I'll take any questions if there are any. Thank you very much. Thank you.
Thank you, Bill. Please use the Q&A button to ask any questions you have. We have one that's come in so far. What does the carbon footprint look like in comparison between incineration and Cambi with anaerobic digestion?
Yes, great question. Yeah, what I didn't really go over too much detail was that the model that was developed is a comparative model. So it looks at pretty much anything you can do with biosolids, including drying and incineration and all these things. Incineration has quite a high carbon footprint by itself. But if you did digestion and thermal hydrolysis with digestion prior to incineration, you can even though you're doing a lot more stuff and a lot more processing and liquid treatment and steam consumption, or even accounting for all of that, you can have a massive reduction in carbon footprint in the incinerator, not to mention increasing the capacity of the incinerator. So, well, I used to work United Utilities, put thermal hydrolysis prior to incineration. Subsequently, that incinerator's been shut down. There are other incinerators with thermal hydrolysis where they've seen huge benefits and huge reductions. A lot of it really, as a surrogate measure, is operating costs. So the lower those are, typically, the lower the environmental impact. If I'm using less electricity, I'm using less gas, I have less biosolids. If I'm incinerating, I'm using fewer chemicals for flue gas abatement systems. If I use less, I'm likely to have a lower carbon footprint and lower operating costs. So digestion, overall, comparing multiple technologies, digestion to land application will result typically in the lowest carbon footprint of any biosolids outlet. And the better the digestion, the lower the carbon footprint.
Good, thank you, Bill. No other questions have come in. So for now, let's go ahead and if you could stop sharing your screen and we'll
work that
get...
out. Thank you. Stop share, there we go.
So please do, if you have any more questions, please do continue to reach out and use the Q&A feature just for our speakers, or if we have time at the very, very end. So our final presenter today is Tom Darby, and he is speaking on the Hermitage experience with food waste supplementation. Before becoming manager of the Hermitage Municipal Authority in 1985, Tom worked for Northwest Engineering, a civil engineering firm located in Northwest Pennsylvania, for more than 7 years as a project manager of municipal construction projects. In 1988, Tom also became the superintendent of the City of Hermitage's Water Pollution Control Department. So Tom, do you want to turn on your video and we'll hand it on over to you?
Okay, very good. Can you hear me?
Sure can.
All right, I'm glad to be here. So if you were at Baltimore a few years ago, you were able to hear my presentation there on what we're doing in Hermitage, Pennsylvania with our food waste to energy facility. In 2014, we began operating our new facility with the Suez two-pad system, where we incorporate the thermophilic digester and mesophilic digestion. That has been operating very well. We have gone through some bumps and experienced some highs and lows, but overall we continue to produce a Class A EQ biosolid, which we were able to have removed from the facility at a very reasonable price where it is land applied. And in addition to that, we're able to generate electricity. Our facility is now handling anywhere between 3,500 and 4,000 tons of solid food waste per year, and typically treating 2.5 to 3 million gallons of liquid organics per year. And that material comes to us through a multitude of sources that find us through conversations that we have. We have different companies who contact us as more or less as brokers who have pre-consumer organics, expired product that is off quality, doesn't meet the consumer's standard, and we're able to take that, and the advantage that we have with doing that is that we're able to generate revenue through the receiving of this material and depacking it and feeding it to our digesters. In the process of that, we also are able to generate electricity, and we're currently averaging about 300,000 kilowatt hours per month of exported power. And by the way, that goes a long way towards our reducing our carbon footprint. And our monthly biogas production is roughly around 2 million cubic feet of biomethane gas. We utilize that in a 600 kW engine at the moment. We're supplementing that now with a new 375 kW Nissan engine that will be able to run 100% on biogas, and will continue to generate enough electricity to offset our needs for our facility. And just to put that into perspective, our facility's monthly electric bill, let me back up. We are a 7 MGD rated plant. We average about 3.5 MGD over the year. So we have plenty of capacity, but our power needs from the electrical side is about $25,000 to $32,000 per month. We're offsetting that with the amount of energy that we're able to produce by supplementing our digesters with organics. If we were only to run on the wastewater biosolids, what we've determined is that we would be only generating about 20 to 30,000 cubic feet of biogas on a daily basis. So the organics aspect of it has been a win for us. It was not something that we went into the upgrade with the intention of doing. We wanted to boost our biogas so that we could utilize it. We didn't realize how much we would be able to generate. But as one thing turned into another, it has been a domino effect. We started out with a depacker that only perforated material, liquid materials. In this case, it was bottled milk, soda, anything that would flow. We found that the demand for disposal was also very great in the solid organics. So packaged products, material that are in cases, in cardboard, in plastic, and even in aluminum cans, was also there was also a need to dispose of that. And so we upgraded. We went to a Scott's turbo separator, and that met our needs, and it continues to work very well for us. But then in August of last year, we took possession for a pilot program for Veolia of a e-cruiser, which is a large screw type organics depackager. And this has a completely different capability, and we're able to feed product into that and extract the organics from the packaging, but not shatter the plastics as much as we were doing in some of the other operations. So the operation continues to grow. We continue to diversify. Our revenue stream has increased because of our capabilities. We have the ability to probably do, we're estimating between 6,000 and 10,000 tons of organics per year. One of our recent disposals was with the COVID situation going on. Pubs and restaurants and bars were not able to serve beer, draft beer in particular, and so we were able to receive over 130,000 gallons of beer that had been put into kegs that wasn't able to be distributed. So we took that, and I might add that it does a tremendous job at making gas. Some of our upgrades that we're looking at in the very near future, we have a contract out now for new gas domes on two of our 3 mesophilic digesters. We are installing at this time the 375 kW biogas generator from Nissan. We have purchased the Veolia e-Cruiser, and we'll be setting that up in its permanent location. We have, over the last year, begun replacing. Now, this is a negative to what we originally started out with. Many of the piping systems that were installed were ductile iron. They were never the right choice for the acidic environment. And so we're basically just destroyed by that. And now we've replaced most everything, including pump impellers, with stainless steel. The other thing that we have out for bid also is a new 100,000 cubic foot storage vessel. This would be just a large ball that we'll be able to store excess gas in, with the idea of, in the future, pulling that gas off and running it through a CNG process, and be able to produce CNG for some of our city's vehicles. The other projects that we're looking at in the future will involve a post-food waste collection network to bring organics into the facility. Pretty much everything that we take now is pre-consumer, so it's never gone into the restaurants or into residents' homes or anything like that. It's everything that has not been able to be sold for whatever reason. But we're now looking at taking food waste from restaurants, even residential, if we can manage the transportation system for that. We want that all to be operated by vehicles that are powered by our energy, whether it be electric vehicles or CNG. And then one third option that is a possibility for us would be pipeline injection. That's probably the lowest on our priority list. I will say again that we generate a Class EV biosolid. I believe we're the only municipal facility in the state of Pennsylvania doing that. We also just recently received the Pennsylvania Governor's Award for local community innovative technology for our facility. I don't know that I really have too much else to say. If you've got questions, I'd be more than happy to answer them.
Thanks, Tom. So I actually had a question for you.
Sure.
Regarding kind of digester operations, how do you equalize what's going into your digesters, knowing, whether or not you're getting beer that week or ice cream the next week?
Yeah.
From operating a biosolids digester to one that's so heavily food waste, what do you have to do to operate your digesters differently to keep them healthy?
Well, that's a good question. So if you think about the system, it's pretty much a human body. It needs calories. It needs to be able to generate energy, which is what we're taking and turning into electricity. We will take in a product that doesn't generate energy. We've taken bottled water with flavorings in them that has absolutely no energy value in it or organics whatsoever. We're getting revenue because we're taking it, we're depacking it, we're disposing of the liquids through the wastewater plant, and then disposing of the plastics, or if it's aluminum, we can recycle that. But we have pretty much been able to balance everything. We feed 3 times a day. So we feed in the morning, we feed in the afternoon, we feed at night, and we split all the food goes into the pre-sequence tanks, the feed sequence tank, and then it's blended with the wastewater biosolids and fed into the thermophilic digester. That's where the real process begins, as you all well know. The bugs take over. We're running them around 140 degrees. And then from there, we distribute it into a balance between 1 and 2 digester, and then 2 and 3, and then 3 and 1. And that has been able to maintain for us our consistent biosolids. We pull them off and run them through a belt filter press. So it's tricky. We know that, for instance, we get dairy products 3-4 truckloads a week, 40,000 pounds each one. It's bottled milk, it's cottage cheese and sour cream. We get dog food, bulk dog food, which again is a great gas producer. But it's a dry mix, so we'll blend that with the dairy product, or if there's beer or soda or anything like that. The other things are pluses for us. We've done 2,055-gallon drums of honey, fake honey that was confiscated from outside of the United States. Well, it was confiscated in the U.S., but brought in from outside. Mm-hmm. Ice cream, I mentioned at my last presentation, we've done 300 tons of ice cream. Again, you blend that with other products to create a better product to be blended with the wastewater biosolids.
Okay, thank you.
Yep.
We have time for one more really quick question before we have to close up. How are you financing the purchase of the equipment you're using in your cogen system?
We did a bond issue, and that's the beauty of being a municipal operation. We can do bond issues. I will say that because we generate power, we're making revenue. We have not had a rate increase in over 5 years, and we're not looking at one in the next 1 to 2 years, even with the bond issue. We also refunded a recent bond issue, which gave us extra money that allowed us to maintain our rates as they are now. It's through the municipal bond market.
All right. Well, thank you so much. I'm afraid we are out of time for today. So I want to thank everybody for being here. I want to thank Tom and Bill and Chris for presenting today. A link to the recorded webinars will be sent out at the end of the entire series in mid-August. And a last plug for our upcoming talks. We have 4 more in this webinar series on for the Mid-Atlantic Biosolids Association this Thursday and the next Tuesday and Thursday. And the last one is on Tuesday, August the 4th. So please do come back and learn more about biosolids and advanced stabilization and all of the great topics. So thanks again. I appreciate it. Have a great day.